Unit 7 in Algebra 3 is all about trigonometry. In fact, we're gonna split trigonometry actually up over three different units. The Unit 7 we'll talk and review a bit of our right triangle trig, and then explore some of our trig ratios, and to go a little bit more into depth and explore something called the unit circle. In Unit 8, we will talk about some of our properties of trigonometry, look at identifying values, area, and such of unknowns in triangles, in and out of triangles. And then in Unit 9, we're going to look at graphing our trig functions. So welcome to trigonometry. So when we think about trigonometry, I want you to think about it being associated with a triangle. And so that's first thing to talk about. But the idea is trigonometry is a study or a branch of mathematics that we use to find unknowns, not unlike any of our other branches, but unknowns associated with triangles. And so the idea that we might need to find, I don't know, the length across a river or a canyon or a valley, or the distance from one town to the next. And we might be a computer generator or a statistician or somebody that is trying to compute missing values. We might use trigonometry to find those. And so basically we can relate any distance as a point in a coordinate plane, and then from there we can use it as a rotation around an origin. And then it comes back to these special properties about right triangles that we are going to learn in this first unit. All right, so first thing I want to do is just go back to some geometry real quick. This is right triangle trig. This is something that you looked at a long time ago, or whenever you had your geometry course. And basically it says that, hey, if we have a triangle and we have a right triangle, that's a triangle with a 90-degree corner, that there are some pieces of it that we can identify. First of all, this side, this side here that is directly across from the right angle is called the hypotenuse. All right, that's going to be important to know. Then also these other two sides, these are called legs, or just leg, plural. These two sides that are connected to our right angle are called the legs of the triangle. And a long time ago, thousands of years ago, a guy by the name of Pythagoras came up with this relationship that's true for all triangles, whether they're a triangle in Greece thousands of years ago or a triangle in Stillwater, Minnesota. This is true for every single triangle out there. These are the legs. If we take the legs and we square them and take the sum of them, it's always equal to the hypotenuse squared. Okay? So we'll talk a little bit about that, and we're just going to review those. These should be pretty quick. So for example, find the third side in simplest radical form. So if we're going to find this side right here, let's call this C. This is the hypotenuse. By the way, these are the legs. So we were able to, and this is from geometry, just reviewing, we're able to square those, take the sum of those, and that's equal to this third side. All right, so I'll do the math for you. Use your calculator. Final step, take the square root of 242. And we don't need to do plus or minus because we're looking for just the positive version, because this is a length here. And then
so the last thing that you do when you put it in simplified radical form, you have to look and see if you can find any perfect square that's a factor of this number right here. So 11 times 11 is 121. And 121 times 2 is 242. So what I'm going to do is I'm going to simplify this. Square root of 121 is 11. Root 2 is irrational. Final answer is 11 roots of 2. And we do want, that's a small detail in Algebra 3 that we think is important. Make sure we put it in simplest radical form.
Okay, so what happens here is if we have a missing leg, let's just call that A. So to compute this, we have a squared plus b squared equals c squared. Slightly different than this problem here. In this example here, we're going to subtract the 9 from the 15 squared. So we get a squared equals 216. Again, I'm moving fast just because it is a bit of review. This is square root of 216. Here is an example where 36, which is a perfect square, times 6 is a factor of 216. We did this earlier this year. So final is 6 square root of 6. This is called simplified radical form. This is using the Pythagorean theorem. We also did some word problems in geometry like this. So let's say we were right here. We got into a car and we drove north 21 miles. Then we drove east 20 miles. We might ask you, hey, how far is this distance? Well, we can relate this to a right triangle. Pythagorean theorem applies. Oh, I should have some arms here. Applies for any right triangle in the world. So I could compute this distance by looking at these two values here, saying these are the legs, this is the hypotenuse. And so Pythagorean theorem holds true here. This is 841. Square root of 841 is 29. And so in this case, it's a distance, 29 miles. Same idea here. You did some of these problems. This is kind of maybe a problem you might see on the ACT. Let's call this our wall. And then let's say we know that wall is how tall? We know that wall is 24 feet. So the distance from here to here is 24 feet. We put a ladder up there. And this ladder is 25 feet. How many feet from the bottom of the ladder to the bottom of the building? So we're looking for this right here. This is, if we think about this as a right triangle, these are my legs. Let's just call this A. So we have Pythagorean theorem again. And by the way, Pythagorean theorem is all over the place in mathematics, especially in trigonometry. So we compute this, we get A squared equals 49. I'll let you guys do those calculations on your calculator. And we finally get the length is 7 feet. Okay, that is review from geometry, but it is important to talk a little bit about that. So here's what happens now. In trigonometry, we have something called our basic 3 trig ratios. So these are super important, and we want to spend some time with these. These ratios compare the lengths of two sides in one angle, all right? They're consistent, meaning they're a ratio, so they can either be larger or smaller. It doesn't matter how big the triangle is. It just has to be a right triangle. And then these ratios have to do with these specific sides. The one side that doesn't ever change is the side across from the right angle. That's always called the hypotenuse. These other sides are legs, depending upon which acute angle we're looking at. So theta is traditionally used to represent an acute angle in the triangle. There's 2 of them. It could be this angle A, and by the way, capital letters are used to represent an angle in geometry. Also, lowercase letters are used to represent a side length, or angle B. Okay, so if we're looking at angle A, this leg right here is called the adjacent leg. The other leg, the one that is connected to the 90, the other leg is called the opposite leg. Now, if we switch and we look at angle B, this side becomes the adjacent leg, and this side becomes the opposite leg. All right, so depending upon what angle, what acute angle we're looking at here. All right, so let's just back up a step here. And let's take a look at what our 3 ratios are. And again, we'll have to commit these to memory. So the sine, S-I-N-E, of an angle is the ratio of the opposite to the hypotenuse. And when we say that, this is what we mean by that, the ratio of the opposite to the hypotenuse. So sine of the angle, theta is the angle, we can use capital letters to represent that, is equal to the opposite side, this is the opposite side over the hypotenuse. And again, this is for all triangles. One way we remember that is this word SOH, S-O-H. Sine equals O for opposite, H for hypotenuse, and the order they come in creates the ratio. Okay, our second trig ratio is cosine. The cosine of an angle, abbreviated cos, C-O-S. Theta is any angle, any acute angle. And so if we're looking at specific to A, the adjacent and opposite side are labeled here. But ca is the ratio shortcut we're going to use, adjacent, A for adjacent, over H hypotenuse. And then our last one is tangent. Tangent of any angle is the opposite over adjacent. The word we're going to use to memorize that is TOA. So you might hear this. This might be something worth repeating. So, ka, toa. So, ka, toa. So, ka, toa. So, ka, toa. Anyways, however you remember it, that's something that's going to help us commit these three ratios to memory. And again, a ratio is just a fraction that compares two sides in a right triangle, and these are very specific sides. Okay, so these first couple examples, we want you to write the ratio in simplest radical form. All right, so in this example, find the exact value of cosine A in simplest radical form. So for me to do this, what I think about cosine, think about ka. And so I write this down. I circle angle A, or sometimes I just put this little dash so I know what side's what side is which. This is the hypotenuse side. I like to label that. Sometimes I just use an H. This leg down here, now there's two legs. They're very specific. The leg that is connected to the acute angle is called the adjacent side. This side that's opposite it, that's connected to the right angle, is called the opposite side. And I'm going to use this mnemonic tool, I guess we maybe call it ka, cosine of angle A equals AH. So A in order, the adjacent side over the hypotenuse side. Simplify it. If it's simplified, we're done. Okay, 3/5 is obviously simplified. Simplified, there's no radicals there, so we're good to go. Let's try another one. Sine. Think about so. So, ka, toa. So I like to write it down. I like to circle angle A. I like to label my sides. This is the adjacent side. This is my hypotenuse side. This is the opposite side. And so sine of A equals, we don't know that angle. We're just saying the sine of it's going to always be this ratio, the opposite over hypotenuse. So here's my opposite side. That's why I like to label them over my hypotenuse. Let's simplify. 8/12 can be simplified to 2/3. Final. There's my ratio. We don't want to write that ratio as a decimal, by the way. It could be a whole number if we cancel out and have just a 1 on the bottom. But otherwise, we want to leave it in simplified fraction or radical form. Find the exact value of tangent A. Again, we're going to use our device. So katoa. I like to write this down. I circle angle A. I label my sides, opposite, adjacent, hypotenuse. Okay, and then I write this out. Tangent of angle A equals OA. So opposite is √75. A adjacent is 5. Now I need to simplify a little bit using my radical properties that we studied earlier this year. Square root of 75 can be square root of 25 times 3, which can be 5√3. Ooh, this is exciting because boom, common multiple. Final answer here, the ratio is square root 3/1, which we would just write square root 3. One more for us here before we kind of move on. Cosine ka, so ka, toa. I'm looking for the adjacent and hypotenuse side of angle A. Here's angle A. This is my adjacent side. This is my hypotenuse side. So cosine, COS, angle A equals adjacent over hypotenuse. Last example I wanted to show you, we know from our radical work before, we can't have this. So in other words, we have to rationalize the denominator. The one way we do that is we multiply the top and the bottom by that root. Simplify that. This is 3√13. The bottom is √13 times √13 is √13 squared. So the roots go away. And then just look, are there any common multiples here between 3 and 13? 13 is prime. I'm done. That's simplified radical form. Last but not least, if we commit those first 3 trig ratios to memory and we go so sine is so, ka for cosine, toa, there are three what we call reciprocal trig ratios. So if I memorize the first three, here's what happens. The next three are related to each other. So this one is called cosecant, abbreviated CSC. And the one thing I think about is it's the reciprocal of sine, which means sine is opposite over hypotenuse. So I invert O and H. I switch the order here. So this is SHO for this one. So it's hypotenuse over opposite. And secant, this next one here, is this value. It's the inverse or the reciprocal of this. So instead of A over H, the reciprocal, we just flip it, is H over A. And then cotangent, abbreviated COT, is the reciprocal of tangent. So we flip O and A. Remember, these are ratios, so instead of over A, it's A over O. Okay, so I'll show you how I go about these. Again, we want to try to commit these to memory. If we have to keep looking back at our first three trig ratios, it's going to really, really slow us down and hinder our progress. So here's an example right here. It says we have a triangle. It gives you measurements. And just to remember from geometry, capital T angle measure, we can represent the side length using both angles. So TS would be, this side length would be 60, or we can use a small little letter. This could be little r. It's the angle across from it, lowercase. So this would be little s, and this one would be little t. All right, so just something to think about. But anyways, this says what ratio represents cotangent of angle S. So the thing I like to think about is try to commit these to memory. Cotangent is the reciprocal of tangent. So I think about TOA, and then I'm going to think about flipping or finding the reciprocal. Instead of opposite over adjacent, I'm going to flip those and go adjacent over opposite. So we'll start off with cotangent. It says angle S, so I'm going to circle angle S right here. So cotangent angle S equals. And now instead of opposite over adjacent, I'm going to go adjacent. So I'll label my sides over opposite. This is my adjacent side. This is my opposite side. So it's 65 over 72. And that's it. I'm not really doing too much more after that. All I'm doing here is just simplifying that fraction. If it's simplified, then we're good to go. Let's do another one here. So what ratio represents cosecant? My angle's given here. I'm going to label this angle. Cosecant is the reciprocal of sine. So I'm going to write that down. That's my mnemonic device, my memory device. I'm going to flip the O and the H. So I need the opposite side. Let's see. My opposite side is here. This is my hypotenuse. So when I do my ratio here, I'm going to use cosecant, CSC, of angle U equals, flip these. So go hypotenuse first over opposite. Again, simplify. If you don't know if that's simplified, you guys type it in your calculator and use the fraction mode. One more, and we haven't done this one, secant. So secant is the reciprocal of cosine. Ca is my memory device. I'm going to flip A and H. So we'll use the same triangle here. This is my adjacent side. I already have my hypotenuse side labeled. So secant of angle T. Oh, let's get crazy here. This is angle T. So this is not my adjacent side. This is not the angle I'm looking at. I am looking at this angle down here, which changes things. So this side now, this leg becomes my adjacent side, and this side becomes my opposite side. Be careful. Okay? So I still have my hypotenuse opposite. So secant, I'm going to flip these over of angle T. Let's clean this up just a little bit. So angle T equals hypotenuse over adjacent. So 53 over adjacent. And then I simplify that, done deal, there. Now you'll notice we do have some ratios that are the same using a different trig ratio, and that's because these angles are different. And the reason why the ratio is consistent, because we have three angles in this triangle. These two here have to add to 90, and if we know one, we can subtract from 90 to find the other. Okay, so there's some special relationships we're going to look at.